Hello friends, today we're going to be looking at topic 2.5, which is exponential function context. So looking at transformations, other ways of rewriting functions given a particular function or given some information, and then also using data modeling. So we'll be going back to Desmos calculator to look at regression models, but exponential style. So sometimes when you look at a data set, it doesn't look like an exponential function right away. When you're looking at going from that one output to the next output, it doesn't look like it's following the exponential pattern. But sometimes what's happening is that you just have to add a value, right? Or add or subtract something from the output values, and then it does give that to you. You see the exponential. So one way to find that is to look at the differences, what we've done before with a lot of these types of functions. And so that's what I've done here. I've prepared, for example, 1a, you can see the difference here is 6, 12, 24. So when we see that that's the difference that's taking place, and we realize, well, wait a minute, if we just subtract 1 from this, then we do end up with an exponential function, right? Or what looks like an exponential growth pattern. So I can add a column here, f of x, but f of x minus 1. So I see 6, 12, 24, 48, 96. That does follow the pattern where the common ratio, the thing that's being multiplied each time, is 2. And my initial value is 6. So what this looks like is f of x, or rather, I can write f of x minus 1 equals 6 times 2 to the x. Right? And so my f of x is just 6 times 2 to the x plus 1. So that's where that's the function for that for the function that we're seeing, the equation for the function that we're seeing. Let's take a look at the next one. And here again we see that 2 times, I don't know what would be 10, and then 10 times would be 34. That's not working out. But if we look at the differences again, we get 8, 24, 72. So 24 is 8 times 3. 72 is 24 times 3. And 216 is 72 times 3. Okay, so what we have here is a common ratio of 3. But what's happening is that we have to, what do we have to add in order to get something like this to happen? Well, something near 2, like what could I multiply by to get something that would be kind of near 10? If I add 2, I get 4 and then 12, right? So 4 times 3 is 12. So I know the common ratio is 3 from looking at the differences, and then so I can ask myself, 4 times 3 would give me 12. So that way I'm just adding 2 to each of these, and that works. So I'm going to create a new column, and now I can see 4 times 3 is 12, times 3 is 36, etc. So the common ratio is 3, and my initial value, right, when x is 0, is 4. Right? And so g of x plus 2 equals 4 times 3 to the x power. That means that g of x is equal to 4 times 3 to the x power minus 2. Next one. So here, again, I'm not seeing any pattern emerging immediately just from the numbers themselves, but when I subtract, right, I take the differences, then I see that I've got 32, 16, those are the differences there. And that is, I'm cutting in half each time. So here the common ratio is 1/2. And all I have to do is add 1 to each of these values. I get 64, 32, 16. Those are values that are each half of the other. So now I'm going to write h of x plus 1, and I get 64, 32, 16, 8, and 4. I have a common ratio of 1/2, and I have an initial value of 64. h of x plus 1 equals 64 times 1/2 to the x power. Another way of writing this would be to say it's 64 times 2 to the negative 1 times x, which would be 64 times 2 to the negative x. We can write it that way. So then h of x could be 64 times 2 to the negative x minus 1. And we can also find, like we've seen before, kind of like with the geometric ratios, that if we have two of the values, right, two inputs and two outputs, a pair of coordinates, you could say, then we can find the function from that. Here's an example. So imagine that for the first 30 minutes of they let people into a stadium, and for the first 30 minutes, the number of people in the stadium can be modeled according to a particular exponential function. And here we're given two of these values, right? So after 2 minutes, there are 47 people in the stadium. And after 20 minutes, there's 2,602 fans inside the stadium after the doors open. It says, use the given data to write two equations that can be used to find the values for constants a and b in the expression. Okay, well, I know that f of 2 equals, now there's some initial value and there's some common ratio. We don't know what they are, right? Equals a times b to the 2 squared, right? I'm putting in 2 as the time, and this is equal to 47. Okay, and then also f of 20 equals some initial value times some common ratio to the 20 power, because it's after 20 minutes, and that's equal to 2,602 fans inside of the stadium. Okay, now if I were to try to get a and b just algebraically, kind of by hand, it would be way too complicated to do that. So I go to Desmos. Okay, and that's what the function looks like. That's not very helpful right now, but again, remember that we can find the regression model. Initially, it gives us a linear regression, but that's not very helpful. We know that this is exponential, and so we're going to choose an exponential regression, and it gives us this equation. So now I have the equation, right? Y equals 30.089 times 1.2498 to the x power. The initial value is roughly 30, and the common ratio is 1.2498. And they give us these values right here. Right. And again, each calculator might be a little bit different. This one should be pretty much the same because it's only 2 points that we're modeling. But if you've got a bunch of points we saw before, comes out, could be just slightly different, but should be close. Let's try example 3. Same kind of situation, right? So the way that we set this up, write two equations. So we know that g of 3 is the input, equals a times b to the 3, which is 21.54. And also g of 8 is a times b to the 8th, which is 3.62. Okay, this looks like exponential decay, right? As the input's going up, the output value is going down. Again, let's use Desmos to figure this out. Here's our regression model, and you can see it's already put it in the exponential regression. All I did was I went back to the other table and I put in the new values, and the exponential regression is already there. So I can see that my value for A is 62.8, and my value for B, the common ratio, you could call it, is 0.7. The base is 0.7. So A, initial value, was 62.8, and B was 0.7. Okay, so here we're introducing also a number that comes up very often in a bunch of different types of ways. It's called the natural base. E sometimes is called the natural number, Euler's number. It was first kind of discovered by Bernoulli. He was looking at these growth rates, and he had a function where he was solving for it, or look, as n to it went to infinity and it approximated E. Euler also came up with another expression for it based on a summation. So, but anyway, it shows up a lot in like finance, interest rates, that kind of thing. And in physics, in AP Physics C, another class that I teach, it shows up in the drag equation. So the exponential functions we have for describing drag and force and velocity and that kind of thing, then the velocity, as the velocity changes when there is a drag force, E shows up. And so it's one of these interesting numbers that just keeps popping up in all these places that seem to be totally unconnected. part of the beauty of math and how it integrates into physics and other things, right? It's amazing that we can use math to describe the natural world. It doesn't have to be that way, but it is. Incredible. All right. So here's an example. It says that the number of bacteria in a particular culture can be modeled by the exponential function 17 times e to the 0.31 t, right, where t is measured in hours. So it says let a of t equals a times b of t. So notice a of t is different from b of t, but let it be an equivalent expression for b of t. Find the value of b. So actually in this here it says find the value of b, but this should be crossed out, and we should actually be trying to find the value of a. Okay, it's in the answer key, it's not in the packet. Maybe a typo. All right, so it says a of t equals a times b to the t. All right, well, a of 0 is going to be equal to b of 0. And so b of 0, that would be 17 times e to the 0.31 times 0. And so this is just 1. And so this is going to be equal to 17. I want the same value when I plug in 0 for a of 0. So that means that lowercase a, right, the initial value is going to be the same for both, and that's got to be 17 also for big A of t. It says find the average rate of change of b of t over the interval from 1 to 7 hours. Okay, average rate of change basically is like the slope. We're taking 2 points and we're just finding the slope between those 2 points. So all I have to do here is find b of 1 and b of 7. And remember, so it's like slope, right? So rise over run. And so I'll take these two values and I can put them into basically the slope formula, right? The rise is given by the output and the run is given by the input. When you do this calculation, it's a little messy with the calculator, but you can get it. It's 20.95. So now for example C, we're going to cross this out because finding the number of bacteria after 15 hours, that's easy. But instead, we're going to do this. We're going to find the time when the number reaches 1,000. Okay, so I want to find the input that's going to give me the output of 1,000. So we go back to Desmos. So the way I do it is I plug in the function, and you can see that's the red line. And then I plug in the line y equals 1,000. And what I do is I click on the place where they intersect. I click on that point, and it gives me the input-output. So the population will reach 1,000 after 13.14 hours, roughly. Similar example, 5 having to do with population growth. After 50 deer were introduced into a large wooded area, the population of the deer can be modeled using an exponential function, a times b to the t. So it doesn't give us what the initial value and what the base are. But we do know that the population of deer increased by 13% each year. Well, we know that 50 deer were introduced, right? And so a is the initial value. A has to equal 50. You can think of it this way, right? D of 0 has to be equal to 50. That means a times b to the 0 equals 50. Well, b to the 0 is 1, so a has to be 50. Now for b, we know that the population has increased 113% after 1 year. Okay, so the base, what we're multiplying by every time, is 1.13, 113%. So we're doing it like for the first year, you take 50 and you multiply it by 1.13, and that'll give you the number of deer after 1 year. So that means that the base is also is 1.13. That's not a 3. Okay, so d of t is equal to 50 times 1.13 t. According to the model, what is the population of the deer after 6 years? So you would just find d of 6 equals 50 times 1.13 to the 6th power. This is roughly 37.0 1.68 deer. So many there are. And then it says, so C asks us to find an equivalent expression where t is measured in months instead of years. Okay, well, if we think about this, I want it to give me the same value for what I have here, but this is measured in years. I want it to be in months. So whatever goes into the exponent, when I put in 12 months, I want that to equal 1 year. And so if I take the exponent and I divide it by 12, so t over 12, that'll give me the same results, right? Imagine if I put in 12 months, that gives me the same result as 1 year. I don't have to change any other numbers there, right? The initial value, the base, because I know that after 12 months, it's changing by a factor of 1.13. There's another question here in the answer key that I'd like to look at. And so in the answer key, this is actually D. Question C asks, when does the population reach 5,000 deer? Okay. And again, we can use the same trick that we used before with Desmos. So here again, I put in the function, the exponential function, I put in y equals 5,000, and I'm looking for the intersection point. I just click on it, and it gives me the value. So I know that there will be 5,000 deer after roughly 37.68 years. Okay, so a couple of topics in there. Manipulating, rewriting these exponential functions, and also data modeling, putting them into Desmos, using the regression models, and using Desmos to find input values when we're given an output. Thanks for watching. Don't forget to like and subscribe.